Thank you everybody for coming along to my talk. Quick poll, be honest, how many of you came because I said I had a PubConf ticket to give away? Good, good. I also do have a PubConf ticket to give away, so you've got to stay for the whole talk though, and there'll be a short quiz in order to be able to win it later. But hello everybody, I'm Hayley. I'm here to give a talk about the computer science behind colour. I am about to get very carried away with this topic, but before I do, I just want to give a really big thank you to all of the sponsors who put NDC together. I am one of the Perth crew. Apparently there is a big pack of us, but I think I'm slightly cooler because I actually come from a town, a teeny tiny town 3 hours south of Perth. So I think I'm prepared to claim that I travelled the furthest to get here. I haven't heard of anyone travelling further yet. So thank you so much, sponsors, for funding this. Obviously couldn't be here without you. So, like I said, hello, my name's Hayley. I am a senior engineer and a developer mentor at Envato. Has anyone here heard of Envato before? Oh, yes, cool. Even if you haven't heard of us, chances are you've actually seen our stuff used. We're incredibly popular. So basically, if you are a digital creator, so you create graphic art or sound effects or short videos or whatever, you can sell your creations on one of Envato's platforms and make money from it. And we have made millions of dollars for creators around the world, which is really, really cool. But at Envato, like I said, I'm a senior engineer, but the cooler part of my title is developer mentor. And what that means is I actually have a really cool and really unique role. I spend about 80% of my time teaching apprentice developers and getting them ready for their first role in tech. And this is a program that we've been running at Envato for 5 or 6 years. It's exclusively reserved for women and non-binary as a way to give them a stepping stone into the industry. So I love this job, it's very cool, and the other 20% of my time I spend working on other diversity, equity and inclusion initiatives. So I have been pretty heavily involved in the tech conference meetup world for quite a long time, for like most of my career, working on diversity initiatives. But as part of that, I've spent a significant amount of my time teaching others because long ago, I figured out that if I wanted to get more diverse people into the tech industry, I had to do something about helping them get there in the first place, which involves teaching peeps the very basics. So I have taught, I kid you not, all the way from like 5-year-olds learning how to play with like robots up to teachers near retirement age figuring out how to teach programming to their students. So I have taught nearly all age groups how to program in some capacity over the last 10 years. But yeah, now I get to focus on peeps going to their first tech role, which is really cool. The reason I bring that up though is because I have spent so much of my career with people who are absolutely brand new to tech, it means that I've learned a lot of interesting things about how people perceive our industry. And I think the longer you're in tech, the more you kind of forget how terrifying it can be for those looking at it at the outside. And that's why I want to talk about the computer science behind colour. I want to give you the knowledge and also the tools to pass this knowledge on to others about how colours came to be on computers and why they work the way they work. I really want to demystify that magic behind the computer because, like I said, a lot of people who are new to programming or even new to using a computer, those computers, they're terrifying, magical, know-all boxes that will just shame you if you get something wrong, which is absolutely not true, right? They're seriously stupid. Computers are not smart, they have tantrums all the time, and sometimes you literally just have to turn them off and on again to fix them. They are not wise beings. But for people who aren't in our industry, they do seem like a wise being, and like the world will implode if they do something wrong. So if you have someone in your world who feels that way about computers, I'd love for you to take some of these things away from this talk today and actually explain, no, this is how they work and why they work that way. It's actually for us humans, it's not for computers. In fact, I think one of the wisest words I ever learned from who taught me how to teach other people was, computers are made for humans, they're not made for other computers. But somewhere along the way, some people start to lose track of that idea or have just never thought about how does the thing work on the inside. Which is why it's really cool that we've had lots of talks about actually how do computers work on the inside, and like this morning's keynote about how did the web come to be what it is today. And we're going to take an even deeper dive than that into one particular part of it. So, what are we actually going to talk about? Well, like I said in my abstract and in Slack today, we are going to be playing with paint. We're also going to be playing with flashlights. I called them torches in the speaker channel, but then someone thought that I meant like a stick with fire on the top. So not torches, because apparently that's not the word to use here, like flashlights, like, you know, with batteries in them. And we're going to have a look at how those work when we mix colours with lights. We're going to have a look at the physics of how does light actually move around the room. We're going to look at how do our eyes actually perceive that light and that colour. And then we're going to bring that all into, okay, cool, but how does that relate to computer screens and how does that relate to us as programmers? So we're going to go on quite a journey today. We're going to start all the way back in kindergarten and we're going to go all the way up to a computer science degree. So this is definitely a very whirlwind tour of how this works, but I really hope that you enjoy this presentation. So on that note, before I open the paint, like I said, we're going to start with kindergarten. Now, here's the thing. I have taught all age groups, and I would love for you today to embrace the younger end of those age groups. As in, like, I want you to imagine you're 5 or 6-year-olds, 5 or 6-year-old for this first part. And what I mean by that is, if I show a 5 or 6-year-old something really cool, do you know what they do? They don't just sit there quietly and like nod their head, thank you. They go, ooh, do it again. So I would really love a bit of that today because you're all very scary and like this is quite intimidating. So let's break the ice a little bit. We're just going to do a quick practice round. So just imagine that I just told you the most incredible thing about how computers work. In 3, 2, 1. Yes! Thank you. Okay, I expect that level of enthusiasm for this entire 60-minute talk. You're like, I can't do it, I'm already tired. Okay, all right, let's start playing with paint. So if you think back to kindergarten or primary school, like your very earliest days in the education system or at home or wherever you learned, you might remember learning about mixing paints and something called a colour wheel. So the idea of a colour wheel is to show how colours relate to each other. So this is a simple example, and all it shows is how one colour gradually transitions from one to the next, just in a circle, hence the name colour wheel. So I thought I could point at a bunch of diagrams and stuff with this, or I could just play with some paint because that seemed a lot more fun. So again, you're a tiny little kid, you're learning about paint mixing for the very first time. Let's get started. I apologise if you're watching this from home. This talk really is optimised for in-person, but I will be going back over there shortly. So I got some paint here. I wasn't brave enough to bring this in my suitcase over. I had it in a plastic container in my suitcase and I thought, I can't do this. This will be so bad if it goes wrong. So I went and brought some fresh paint. So I haven't tested these colours before, but actually that leans in really well to something we're going to talk about shortly. So what I'm going to show you is what happens if I mix a couple of colours. And I'll hold this up so you can see in a moment. So I've got a really deep blue here. This is called primary blue. Good, good. And I have yellow. So I'm going to mix that in as well. Okay. There's no real science to the ratio here, although more on that later as well. Some messes have been made. Okay, so I've got blue and yellow. Remember, you're little kids. Watch what happens to this paint. Yeah! Ooh! I know, right? Isn't that the most crazy thing you've ever seen? So this paint, when I mixed blue and yellow, I got green. I know, the shocking stuff. All right, so those are two of my colours that I've mixed together, and now this is going to absolutely blow your mind. So that was yellow and blue. I'm now going to put yellow in again. Okay, so I've got a fresh bowl here. I'm putting some yellow in. And this time, instead of blue, I'm going to get red. Now, this says primary red. To me, it looks really pink, but it says it's red. So I'm going to put some of that in as well. And it's funny, whenever I do this and I look at these two colours in particular, Does anybody else see the sauces from McDonald's? I think it every single time. Okay, so remember, you're 5 or 6 years old. Let's watch what happens. That was like, it started with a commitment, it quickly gave up. Okay, so Makai getting a bit of orange there. Ooh, thank you. Okay, I know, this is shocking. I've never done this before. Okay, so when I mixed blue and yellow, I got green. And when I mixed yellow and red, I got orange. I sincerely hope that wasn't genuinely shocking to any of you, but if it was, then congratulations, we're in kindergarten today. So, I won't do this demo, but also if I was to mix red and blue, I would get purple, thank you. So these three colours that I've talked about, so the red, yellow, and the green, they're actually called primary colours, and I've pointed them out on here. Not only are they primary colours, but they're actually primary colours from the RYB colour model. So yeah, this is the boring online version of this talk. When I mix these colours, these are what I get. So when I say that they're from the RYB colour model, what I mean is a colour model is any system that uses 3 primary colours to create more colours. So my red, yellow, blue, RYB, they were the primary colours that I'm using from this particular colour model. And then the colours that I created by mixing those primaries are called secondary colours. So if I mix 2 primaries, I get a secondary. If I was to mix a primary and a secondary, I can make a tertiary colour. So if I was to mix, say, blue back in with green, so remember this green that I made earlier and we were all really impressed? If I was to mix more blue into this now, this is why I got a tablecloth. So if I'm to mix more blue into this, thank you! So I get a slightly different colour. And I looked this up. The technical name for this colour is blue-green because I've mixed blue and green, and this now creates a tertiary colour. Now, obviously, I could just keep going and get really carried away, and we will again shortly. But basically, what I want to show you is just, they just get deeper and deeper, but we'll start with primary, secondary, tertiary. Okay. Now, the colours that I could create, oh, and there it is there. So the colours that I could create using those particular paints that I have are called a gamut. So a gamut being all the possible colours that I could make with that particular paint. Why that's interesting is, like I said, this is different paint to what I would usually use. Like the paint I use at home is a much darker red. So that means that the gamut of colours that I could produce using that paint is different to the gamut of colours that I can produce using this paint. This becomes more relevant as we get back into screens. It also means that if I switch out one of those for a different brand, I'm going to get a different gamut of colours available to me. Okay, so let's talk a little bit about light. So we were in primary school, or kindergarten even. We're going to just fast forward to high school now, and we're going to talk about physics. But I want you to bring that kindergarten level energy with you, please. Okay, so when we think of light, what we're actually referring to is visible electromagnetic radiation. Big fancy word. The key thing that we're after there is actually the word visible. So that little rainbow on the screen there, that one there. So the electromagnetic spectrum is a range of frequencies covered by electromagnetic radiation, which I think actually came up in one of the talks I went to earlier this week. And it's broken down into different bands of what we call frequencies. Now, if you weren't very good, or physics just wasn't your thing, no worries, got you covered. So when we say frequency, what we're actually referring to is how fast a wave is moving. And in particular, what we actually care about is the wavelength. So that wavelength being the difference between 2 peaks in this wave or 2 troughs in this wave. So what we're actually measuring when we talk about frequency is how many wavelengths are passing a fixed point in a given amount of time. Okay, back to the spectrum. So visible light is only a teeny tiny band on this spectrum. There's a lot of other things whizzing around, but we can only see this visible light. But there are actually many variations of wavelengths within that range. So here's a subset of them. So these different wavelengths are what influence our perception of colour. So when we experience seeing red, we're actually just seeing a long wavelength. And when we experience seeing violet, we're seeing a short wavelength, relatively speaking. So the frequency of a wave is what determines which color we see. But what's the connection between these waves and that paint? We need to talk a little bit about how light moves around a room. So if I go back to my canvas over here, and let me just set your expectations right now. We're just going to be painting lines. I'm not an artist by any stretch of the imagination, so lower those expectations. So what we're going to talk about is, at the moment, that canvas is just white. And in other words, let me put a little diagram up here. In other words, every different wavelength of light is hitting that canvas and bouncing off it. So this canvas is absorbing absolutely no light, which is why we see it is just white. So all those colours are hitting our eyes as one. But when I add some paint to the canvas, so if I add some of my, remember technical name, blue-green, if I add some of this blue-green light, it's a very dark one that I've made. It looks almost green in this purple light here. Thank you! This is really good for my ego. So when I add some light to this, some paint to this canvas now, and what's interesting is mixing with the purple lights, like this is really cool. What's actually happening now is this canvas is absorbing some of the light, and some of the light is being reflected and then hitting our eyes. So in this case, the blue and green wavelengths are hitting our eyes, so we're experiencing blue-green. So that's a white canvas with a little bit of colour on it. But let's talk about the colour black. Now, I experimented with this. So I should be able to use red, yellow, and blue to make black. Turns out that one is relatively scientific and the quantities of each really matters. And I know this because my kitchen turned many shades of nearly black. So I'm just going to cheat a little bit here, and I just actually have some black paint. So it's so funny with the light, it actually looks green to me now. So if I take some of this black paint and I put this on the canvas, we're losing a bit of energy here, people. Like, come on. Okay, so if I put black on the canvas, now something very different is happening. What's happening now is this canvas is actually absorbing all of those wavelengths, and I'm seeing nothing. So all I'm seeing is black. None of those wavelengths are bouncing off and reaching my eyes. So, in other words, we can call this, so starting with a white canvas and adding paint to it is actually called subtractive colour mixing, because less of those wavelengths are able to bounce off and reach my eyes. So, talking about eyes, let's unpack this a little bit more. And I promise you, we're getting closer and closer to how this relates to our job as developers. We're getting there, team. So this is your eye. So if you were to just yank your eye out, slice it in half, this is what you'd see. I mean, that was actually a pretty good, high school reaction. So we're doing well here. Okay, so this, okay, see that green line there? So that part there, the coloured part of your eye, that's called the iris. And that part's relevant and interesting because it is what controls the size of the pupil. The pupil being that thing, if you stare in the mirror and look in your eye, or maybe, turn to the person next to you and stare deeply into their eyes, you can see what looks like that little black hole. So that thing there is called your pupil. And the iris is what controls the size of that pupil, and the size of the pupil defines how much light is going to enter your eye. In front of the iris is the cornea. So that's that squishy thing that covers your eye and therefore stops dirt and all that getting into your eye. So that's just a protective layer. And then on the other side of your eye, of the iris and the pupil, is the lens. And what happens is your cornea and lens work together to help you focus it on objects at varying distances. So that's what lets you, say, get a clear vision of your hand right in front of you and also someone on the other side of your room. You can have that when those two work well together. So, curiously, some people can actually see UV light. So, do I have it? Come on, computer. Here we go. So we have this visible light in the middle of this here, and ultraviolet light is just slightly to the left. There are some people in the world who can actually see UV light if their lens is damaged in a particular way, which can be due to surgery or genetics or a variety of reasons. And when I say some people, I mean there's like 130 cases of this reported. Isn't that incredible? And what a world. It must look so different to those people. Okay, anyway, fun fact that I just found while I was looking up how the eye works. So anyway, the light enters the eye, and when the lens and cornea work well together, that light is then pushed back to the retina, which is like the squishy layer that covers the very back of your eye. So in this picture, this like yellow bit around the back here. So the retina is the lining that covers the back of the eye. It receives light from the lens, and it converts it to electrical neural impulses, which get sent to the brain via the optic nerve, which is this stalk thing at the back here. This thing here. So basically, when the retina and the optic nerve work well together, it's converted to electrical neural impulses, which go to your brain, which is then converted into what we call visual perception. In other words, you get to see stuff. So we're going to focus a little bit more on the retina. The retina is what we're most interested in when it comes to actually perceiving different colours. So the retina contains millions of what we call photoreceptor cells, and those cells are either rods or cones. We're going to start with cones. You have three kinds of cones. They're called S cones, M cones, L cones, or short, medium, long, and what they actually refer to is whether they are sensitive to short, medium, or long wavelengths. So if we recall this wavelength chart from earlier, your SM and L cones are actually sensitive, or most sensitive, to blue, green, and red wavelengths of light, which are, we'll come to that shortly. So if we go back to our paint again, actually, let's test this, because we're in kind of like funky lighting in here, or I am anyway. So I'm going to mix orange. Here we go. So this is my orange, or the McDonald's sauce from earlier. And when I put this on my canvas, so good. Okay, so when I put that on my canvas, what's actually happening is your red and orange cones are being more stimulated than your S&M cones, which is why you're kind of seeing orange. Thank you. You're smashing it with the enthusiasm down the front here. Okay. But on that, as an aside, we are not actually all created equal in any way when it comes to our eyes. So the orange that you're all experiencing when you see that on the canvas is completely different to each other and the orange that I'm experiencing. And that's for a variety of reasons. For some people have colour vision deficiencies. So they have trouble detecting differences between colours or colours at all. But colour deficiencies aside, we all have a different number of cones. So everybody experiences colour in their own way because you all have your own number of SM and L cones and therefore are more sensitive to different wavelengths of light as compared to the person next to you. When I say these cone cells, I mean we have roughly between 6 and 7 million of these cone cells in each eye. So I might have 6.1 million cone cells and you might be on the upper end at 7 million, and therefore the colours that you see are going to be totally different to mine. When I say totally different, relatively speaking, it's probably really, really small, but it's still different to what I see. As well as that, the SM and L cones, they're not actually even evenly distributed amongst each other. So you might have far more S cones than L cones, in which case you would be more sensitive to blue colours than red. So everybody's eyes, totally different. We're all perceiving colours in our own unique way. But on that note, cone cells are really sensitive to colour, but they are not sensitive to light. And that's why we have rod cells. So we have between 6 and 7 million cone cells, but we've got 120 million rod cells because it is really hard to see in the dark. So our rod cells are very sensitive to light, but they have almost no sensitivity to colours, which is why you can't see colours very well in low light, which we can actually see in this room. I mean, I'm slightly blinded up here, but if you look towards the back of the room, you'll notice it's harder to see like reds or oranges or yellows, and everything probably has a slight blue tinge to it, and that's because it's in low light, as opposed to at the front, we're all just seeing purple because we're NDC themed here up the front. So when we're in lower levels of light, we're more sensitive to wavelengths closer to blue, which is why you notice a slight blue tint. Okay, speaking of light, let's look at different methods of mixing colours using light. So I did make some diagrams to explain this, but then I thought, nope, there's a much more fun way to do this. So if we could have the lights off pretty please. Thank you. Okay, so what we're going to do is I have 3 torches, sorry, not sticks with flame. I have 3 flashlights here, and I've put cellophane over them. So by default they were a white light, but I've got a red one, a blue one, and a green one this time. So when I shine the red and blue torches, can you all see that? Thank you! See how when I put them together they make a totally different colour? Yeah, okay. I hope you can you see that? I can see it. There. How about that? Okay, cool. All right. So that's when I mix my red and blue torch, I get magenta. When I shine, let's say red and green, all right, so there's my green, there's my red, and I get yellow. Can we just Thank you. Cool. All right. Anton, could you point this one at the ceiling for me? So Anton's got the blue one. Maybe if we put it up here. Oh, geez, I didn't even know it could do that.
Sorry.
All right. See in the middle there, it's tending to white. It's trying, in the very centre of it, it's going a bit white. But we can also see all the other colours mixing in there as well. Thank you. Thanks. I didn't know it could flash. I don't know how you did that. Okay. We can turn the lights back on. Oh my goodness, that's so purple up here. Okay, so what's interesting there is, once again, I'm using 3 primary colours to make secondary colours. This time I'm just using a different format to do that. So I'm using lights instead of paint. So my primary colours that I used there as well, I used red, green and blue, and I got magenta, cyan and yellow. These colours hopefully sound a little bit familiar to you perhaps. Anybody remember the days of like printers? Like cyan for some reason was always out? Okay. So when we were playing with paint, again, I was using an RYB colour model. When I'm playing with my torches, I'm using an RGB colour model. Does RGB ring any bells here? Cool. More on that later. The difference between these 2 models is when I was using paint, I was using a subtractive colour model. Now when I'm using RGB, I'm using an additive colour model. So basically, our canvas started white, and I had colour subtracted when I added paint, but this time the ceiling started black, as close to black as we could get, and had colour added when we shined lights on it. Okay, talking about lights. So we're getting closer to computer screens now. So, oh, did you look at those overlapping emojis? What? I don't know what's happening there, or that emoji could do that. Something's wrong. Okay, I'm just going to drink water while you all admire my absolutely beautiful pixel art. You got time, like feel free to compliment me. Thank you, I was about to say no one complimented me, okay then. All right, so I want you to imagine your computer screen is just a bunch of teeny tiny little cells. And each of those cells, or those squares, we would call picture elements, and that's where the word pixel comes from. So I have some pixel art here, and so you can imagine that this grid represents my computer screen. And we're just going to zoom in on one particular pixel here. And when we do that, we can see that that pixel is actually represented by 3 lights. A red light, a green light, and a blue light, and in this case, only the blue light is turned on, so I see blue in my picture. So, before we unpack, okay, cool, but what code actually makes that blue, we're going to talk a little bit more about colour models. So, colour models are arbitrary. We use colour spaces to translate them into real life. So we're going to unpack that a little bit. So RGB, the color model that I'm using when I play with torches and the color model that your computer screen uses, more on that in a moment, cannot actually produce every single color. So if you think of this circle as a representation of every single color that you can see, so this is every color in the visible spectrum, RGB actually represents only that kind of wild, like yellow triangular-like shape. Those are all the colors that RGB can produce. So RGB is a color model, and then we have color spaces that are based off this model. So for example, a really common color model is sRGB, or standard RGB, and that was something that was created by HP and Microsoft back in 1996 for use on monitors. I told you we'd come back to the computer part of this. We're getting there. So this was created by HP and Microsoft for use on monitors, and these days it's still really widely used. So unless you have a really modern Apple device, in which case you'll be seeing display P3, but sRGB, oh, that was a fun noise, I don't know how I did that. So sRGB is a device-dependent model. Manufacturers use different color spaces, and there will be slight variations in the materials they use when making those screens as well. So the gamut of colors that your screen can produce will vary compared to a screen produced by another manufacturer. So it's like when we were talking about the paints earlier. If I used a different brand of paint, suddenly I can't produce the same colors, but I can produce new ones instead. Your screens work in the same way. They're not all identical to each other. So it's no coincidence that RGB is the preferred color model for computer screens, because like we talked about earlier, that's the way our cones perceive color. Since we have red, green, and blue cones, our computer screens match that. That's why they use R, G, and B. So it's absolutely no coincidence that they were designed that way. So next we're going to talk a little bit about the math of colors on the web, and then we're going to talk about why we're so thankful that we have math for colors on the web after that. So I've mentioned the red, green, and blue color model a lot. Hopefully that sounds kind of familiar. I'm going to make an assumption that everybody's seen or played with colors at some point in their learning to program career. So I work mainly in the web, as you can tell by this stunning web page. And we're just going to have a play with how the color of this works. Could we have the lights off again? I'm just going to put it, so onto it. Okay, so that's red. We can clearly see that that's red now. And I've just defined that using the RGB function in CSS. So to get red, I had to specify the numbers 255, 0, and 0. That corresponds to 255 red, which is the most that I can have, no green, and no blue. And that gives me a red screen. If I wanted to make a blue screen, I can go 0, and I can say maximum blue, and now I have a blue screen. And just like when I was playing with the torches or the paint, I can change this by mixing up different values. So for example, if I said I wanted 100, that wasn't a very exciting difference. Let's throw some red in there. If I want, let's go 200. Oh, there we go, a nice purple. Cute. That was a genuine one, sorry. I know, I felt it. Okay, cool. So I can give different values between 0 and 255 for the red, green, and blue component and mix them to make different colors. So if we were to zoom in on this web page, you can imagine that when we look at each of those pixels, different amounts of those lights are being turned on and off to mix for us to see these colors. Or rather, those lights are being turned on and off at different intensities. Okay. Ooh. So the range 0 to 255, let's talk about that. That actually comes from binary. Us humans, we don't work in binary, we use a decimal number system, thank goodness, which means that we have 10 digits available to us, so 0 through to 9. Computers, like we said at the beginning of this talk, super dumb, so they use a base 2 number system. So we're just going to have a quick review of how our decimal system works, and we're going to compare it to binary. So if I have only one digit available to me, the highest number that I can represent is 9. If I have 2 digits available to me, the highest number I can represent is 99. If I have 3, the highest number I can represent is 999, and so on. So there's a pattern forming here. Each digit is worth 10 times its digit to the right. So for example, if we look at the number 123, that 1 is worth 100 times as much as the 3. Binary works a little bit differently. Computers, super dumb, they like zeros and ones. So we're going to look at these things called binary digits, and this is where the term bit comes from. So binary digit because they only have 2 values, 0 or 1. So if we take the number 1001, for example, let's try and figure out what that actually translates to for us sensible people who use decimal. Okay, so the 1 is worth 1, the 0 is worth 2, the 0 is worth 4, the 1 is worth 8. So in other words, 1 times 1 plus, did that 2 just disappear? Just gave up. So that we have 1 times 1 plus 0 times 2 plus 0 times 4 plus 1 times 8. So this number is 1 times 8 plus 1 times 1. In other words, 8 plus 1 equals 9. I am going to lose my voice as we go through this, but we're getting there. Okay, let's practice this. So what about this number? We would go 1 times 1 plus 4 times 1 plus 8 times 1. What does this represent in decimal? Be brave. Nice. And what about this number? You answered it first, but you were so not confident, Anton. Like, have more faith in yourself. You got it. Okay. And what about this one? This one's kind of special. Yeah, so this is 15. What's special about this one? Exactly. So if I wanted to represent 16, I have to throw another digit in there. Oh, I pressed a button. Go back, so that's 15. And there's our 16. So if I want to represent 16, I've got to throw another one in. So there is another pattern forming here. So with 2 digits available to me, I can represent 4 different numbers, or up to the number 3, because we start at 0. If I have 3 digits available to me, the highest number that I can represent is 1 plus 2, I want to say 5. It's 7, right? It's 7. It's Friday. So, in other words, 2 to the power of 2 is 4, 2 to the power of 3 is 8. In other words, 2 to the number of bits equals the number of possible combinations. Okay, it's a lot of math. Let's go back to the safe space of our colours. So if we have 8 bits, that gives us the number 255. Doesn't that sound familiar? So we like our bits arranged in 8s. 8 is a good number for a computer, and the highest number that we can represent with 8 bits is 255, and that directly corresponds to the max number that we can give when defining this in our CSS function. Okay, so if we wanted to represent the number 256, we'd have to add another bit, but again, we like our 8s, so we're just going to stick here at 255. Now, an RGB code has 3 components. So it's got its red, its green, and its blue. When we add 8 bits plus 8 bits plus 8 bits, that gives us 24 bits, so we refer to this as 24-bit color. And that gives us the ability to make 16.7 million different colors. That's the total number of combinations that we could create with just those 24 bits. And that is more than enough because humans can only perceive about 10 million different colors, making 24-bit color more than detailed enough for us to use to define colors on a screen. Okay, so 16.7 million colors is a lot. And these days, our screens typically use 24-bit color, which is now known as true color, which gives us all the more reason to use 24-bit color in our CSS. But this was not always the case. We did not have 16.7 million colors at our disposal. Instead, we had a list of named colors, which we still have in CSS today, and they haven't really changed much at all. And this is where things get stupid. So in 1995, 16 basic colors were defined in the HTML 3.0 specification, and these are them. So they were labelled as being in the sRGB color space and were considered the standard 16 colours to be supported by the Windows VGA palette. which is a fancy way of saying a collection of standards created by IBM and adopted for many others as a way of driving displays. So basically, displays had to be able to show these particular colours. And that system was mostly okay, unless you were using Opera 3.5 on Windows 98, in which case 14 colours were randomly missing. Fortunately, by 2005, all modern browsers supported the full list. So we had these 16 standard colours, but we also had 124 extended colours as well. So the idea was that there were 16 colours that should always be supported, and then the other 124 should just probably be supported. Who couldn't see issues with that coming? My God. So also, interestingly, in the CSS 2.1 spec, they randomly promoted orange from an extended colour into the basic colour list, giving us 17 basic colours in total. And then in CSS 3.0, they just threw it out again. So it was only in there for a short amount of time. I don't know what that was about. So these days, the working draft for the next CSS Level 4 colour module combines both lists, so both our basic and our extended, to just have one list called the named colours. But where did these colours come from, you may ask? Well, they came from this. So this is the X window system, which was originally released in 1984, and it included a file called rgb.txt, and this was going to be our downfall. So this file contained a list of color names, which were mapped to RGB color values. Turns out the software was really popular, so they iterated, and in 1987, so 3 years later, X11 was released, and rgb.txt now contains 69 colours. Now, the problem with this is that this list became a really commonly used list of colours, known as the X11 colour names, and these are what are still in CSS today, which led me to discover this extract. Let me read the good parts to you. Note, these colour names are standardised here, not because they are good, but because their use and implementation has been widespread. The names are not even internally consistent. Dark grey is lighter than grey, while light pink is darker than pink. And there's a few other flaws in there as well, which I'll let you read yourself. So basically, these names were not thought through in the slightest. In fact, I did so much digging, and what I could figure out is that it seems to just be this one person who just kind of thought, I like this color, and they'd just throw it in. There was absolutely no consultation process for this. It was this one person who just made this list and didn't think about it. And that is how we ended up with this mess. So they were never intended to become as widely used as they were, which sounds like a lot of our software problems end up from that, it seems. So software was built, they used this list, designers got used to the list, and it became impossible to introduce a new list, so we were kind of stuck at that. On top of that, there was this other separate problem going on. So in the 1990s, most displays were only capable of displaying 256 colours. So operating systems would also often reserve between 16 and 20 colours for their own use. So that meant, I kid you not, that meant that if there was a colour in like a photo or something that the computer didn't recognise, the computer would just like add noise to the image to just make up for the missing colour. Like that was the system that we all decided was the best to use. So basically, there was no consistency between monitors, operating systems, and browsers. Colours were an absolute mess. Enter WebSafe colours. So this was finally a standardised list of 216 colours that we could use on the web. Unfortunately, very shortly after this, computer screens just got better. We got true colour or 24-bit colour, so WebSafe colours weren't needed anymore because we could just use things like our RGB function to pick from 16.7 million colours instead of just our list of 216. So WebSafe colours was definitely needed, it was just really short-lived. Which brings me to hex codes. This is the way that we tend to represent colours on the web these days. Thank you. It reminds me, we can probably have the lights back on now as well. Psst. Lighting guy. Okay, cool. Okay. Oh, I regret that, it's so bright. Okay, so hex codes. Hopefully these look familiar to you, but if they don't, you're about to learn a hell of a lot about them. So a hex code is broken down into 3 components. Here we go. So it's broken down into the red, green, and blue component, which hopefully is starting to seem very familiar to you. So just like RGB, they also have a limit of what we could specify for each of the components. So when we used the RGB function earlier, we could specify up to 255. When we're working in hex, hex codes work just a little bit differently. So they work on a base 16 numbering system. Fortunately, instead of just creating some new digits, we decided just to use the first few letters of the alphabet to fill in those last few digits, which is why we have those letters in our hex codes. That's literally the reason. So that gives us 16 different digits or characters to work with to specify each of these color components, and they're each broken into 2. And so each of these can be converted from this base 16 number into our base 10 numbering system and into binary. So for example, if we take the red component, the number 5 is 0101, and F is 15, so 1111. And I won't make you do all of them, but that's all of them being converted into binary. And this is exactly the reason why we have hex codes. Can you imagine writing that in your CSS? It would be awful. So that's why we have hex codes. That's literally it. I feel like I need to talk more about it, but that's it. That's how hex codes work. So they're just 3 components, each of them translated into binary for the computer to understand which color should be displayed on the screen. Okay. So there are other color models and spaces out there. So we've looked at, in particular, RYB and RGB. No, wait. Red, yellow, blue, red, green, yep. But there are heaps of others. So for example, you might have used HSL before, which is hue, saturation, and lightness. Never made sense to me. We also have the CMY color model, or CMYK color model. That last box is black. It's got kind of a tint of purple on there. Does this one seem familiar? Yeah, so we're going to look at this one a little bit closer. So CMYK, it's considered the industry standard for printing materials. So the K standing for the key color, and it's pretty much always black, because we can't make black with the other 3 colors there, or not a deep enough black. The best you can do is like a really dark brown. So earlier we were playing with paint to get black. Totally didn't just use a tube of black paint. So why not just do that? Why not just use RGB? It's because CMY has a much better range of colors that we can produce when printing. There's also a few other different color models out there, so here's a bunch of them. One of them is a standard for specific American TVs. Don't know why that was necessary, but I threw it on there because it was interesting, so bonus points if you know which one it is. But I don't think a color talk these days would be complete without talking about Pantone. Who here has heard of Pantone? Or maybe like their color of the year thing that they do. Yeah, they're kind of like the Apple of colors. So, like someone here thought that was really controversial, I'm so sorry. So Pantone, it's a company, and it was made famous for making a proprietary color space. And from that they have several different color systems that are each useful for a very specific kind of medium. So their most famous one is probably the Pantone matching system, otherwise known as PMS. Definitely tell that was made by men. And it was specifically created as a way to help printers and designers to more accurately define the colors that they want. So basically, if you were making, say, like some conference swag, you could go to a manufacturer and say, I want this shirt in blue. But who knows what you're going to get back, right? Or you might order it online and click blue, but you don't actually know what that's going to look like when it comes to you in the mail. So the Pantone system was created to kind of fix that problem. So the idea is that you could order these particular cards. We'll talk about these in a second. And from them they define a particular shade from Pantone's color range. And so you could tell your manufacturer, hey, I want Pantone 16, 40, 32. And then you know exactly what color is going to arrive in the mail of the shirt that you're ordering. This is the color space that Pantone is using. So it's a little bit bigger than CMYK, and that's because they have some other colors that they make out from 13 different base pigments to give them a much bigger color space. So if this standardized color system is interesting to you, you can order these cards. And they're literally, it's called like a chip set. They're literally just plastic chips. You pull them out and they have the printed version of what that color will look like. So this is for if you're ordering stuff for primarily for like manufacturing on plastic. If this sounds really good for you and something that you would really want to use and could benefit from using in your company, the good news is these chip sets will only cost £8,000. I kid you not. And for the other Australians in the room, it's about $14,000 for us. So it's not cheap. It's really not cheap. And it gets even better. So £8,000, right? State-of-the-art way of defining colour. The system that you use to index where a card belongs in these columns, it comes on a CD-ROM. I'm serious. It comes on a CD-ROM. Fortunately, it's included, but don't worry, there is another way to give Pantone money. So very recently, Adobe and Pantone had a bit of a falling out. And when I say recently, I mean this was literally November last year, like this is really fresh. So now if you use design software such as like Adobe Illustrator or something, even though you pay for Illustrator, don't worry, you now also have to pay Pantone in order to be able to use Pantone colors in your designs. Otherwise, they'll just render as black. And that goes for previous designs that you've made and saved as well. Like someone was really angry. Like the design community, yeah, they were pretty angry about this. It's ridiculous. Okay, so I could keep talking and talking and talking and talking and talking, but instead I thought we'll have a little bit of a little philosophical ramble instead. So I think it's kind of incredible how something as simple as colours can be so uniquely complicated. For example, I'm looking at my canvas over there and that top one from here, it looks green, but I'm 99% certain I put black paint on there, but it's under the influence of the lights on the stage. So colours are really interesting. I think it's really interesting that they're still in the news at this point in time. It feels like something that we probably should have figured out, but no, they're still being talked about today in our industry. But also, colours are something that seem really simple when you're trying to teach someone how to program. You know, they're building their first web page and they want a blue background. There's so much that goes into creating that blue background, and all of it comes back to how we work as humans. The entire process is mapped back to the cones and rods in our eyes and the colours that we are designed to perceive the most easily. So, why did I make you sit through 60 minutes of this? Number one, you picked this room. That is on you. But also, I picked this because I saw someone on Twitter tweet, oh my god, this is how hex codes work, and they had this really cool thread that explained it. And I realised that, oh my god, people don't know this, because I'm a super nerd who like sits alone in the weekend reading about colours, I don't know. So I thought, you know what, there are probably other people who don't know this as well, which is why I went to write this talk. But this is just one of many, many different talks that we could write to explain the phenomenon of how our computers work, right? They're not these magical beings that absolutely know everything. They're designed by humans and they're designed for humans. So the next time you're working with someone who's getting a little bit frustrated or intimidated by their machine, just remind them of that fact. The computer is seriously stupid, but they're designed by humans for humans. They're here to aid you. They're supposed to work well for you because they were built for you. There's nothing magic about them. Just try not to think too hard about how they effectively run on lightning sand. All right, thank you so much for listening to this talk. I hope you really, really enjoyed it. Thank you for joining me today.